All right, so that was categorical data. Now let's move on to numeric data, and there's more considerations for numeric data just because there's more possible scores on that scale that our observations can take. So when we think about how to summarize numeric data, we just need to think about it a bit differently to how we would do categorical data. As you can see here, the exact same data that we had before, but thinking about our numeric variables, which are PSYC1104 and 105 SNGs. If we were to do a frequency table of those variables, you can see it's actually not particularly useful. And the reason for that is because for numeric variables, there's a greater number of possible observations that a particular score could take. And therefore thinking about how many observations there are for any particular score isn't particularly useful because they tend to be unique scores. So you can see that even though we've only got 6 people here, we've got 1 at 51, 1 at 59, 1 at 62, 1 at 63. It's not a very good way of summarising the information compared to the categorical variables before. So a frequency table is not particularly useful for us here. What we can do instead is to think about these other 3 different aspects in terms of the shape or the pattern of the distribution. So what we're thinking about here is 3 different things, and we mentioned them before. There's the typicality aspect, so what's the most typical score or the most average score? There's variability, which is looking at how much variation or spread or dispersion in scores there are. And there's also the actual pattern of the shape itself. What shape does this particular pattern take? And I'll talk to you about a few different ways that we can think about that. That cat looks very sad. Okay, typicality is the first one we want to think about. So what we're thinking about when we think about typicality is if we had to use one score that would best summarize all the information we have on this particular variable, what score would it be? If we were to pick one score that's most likely to be represented in the data, what score is that going to be? And that's usually the most typical score or the average score. There's a few different ways that we can actually think about typicality, that we can think about average. There's a few different definitions and a few different mathematical calculations for that. So we'll talk about 3 different ways specifically, 3 different types of typicality. The first one is the mean, which is called the arithmetic average. And I'm sure you're very familiar with the concept of an arithmetic average, a mean. You would have done it in high school. We can also think about the median, which you might also be familiar with. The median is the middlemost score if we rank our scores from lowest to highest, and I'll go through the details of how we would actually do that in a second. And the third one is the mode, and the mode is the most common or the most represented scores. Which one is the one that is represented most in our data set? All right, so let's say that we've got a bunch of scores. We've got a bunch of scores here which represent different ages of people in our class. So we've got 7 different scores, 7 different people. We've got ages from all of them. You can see that we've got 19, 19, 21, 29, 18, 17, and 24. So this is a variable age. Age is a numeric variable, so thinking about these kinds of summaries are appropriate to this kind of variable. So if we wanted to calculate the mean age of this particular class, what we would do to calculate the mean, the arithmetic average, is to sum all of them up, to add up all of the ages, all of the scores, and divide by the number of scores that we have, divide by how many observations we've got. So this is just me doing that for you. So you can see we're adding all of the scores up on the numerator of this fraction, divide by the denominator, the number of observations we've got, which is 7, and that gives us a mean score of 21. So we can say here that based on these observations, based on this sample, the average age of our class is 21 years old. And that gives us an idea of what kind of the middle point of this range of scores is. If we wanted to represent the mean, to use a symbol to represent what the mean was, then the symbol that we would use in terms of a sample statistic is going to be this X bar. So X bar is just written here. It's just an italicized X with a line on top of it, X bar. And X bar is the representation of the sample mean. That's the notation that we use if we want to represent the sample mean. If we were doing the same thing but talking about the mean score in the population parameter, then we would use this Greek symbol mu, which is the thing written there. So it's mu bar is the population mean score. As with all of these particular metrics, these particular calculations we can use, they all have pros and cons, they all have pluses and minuses. The advantage of the mean in terms of a measure of typicality is that it's a really common metric. It's a very common calculation that everybody uses. It's the most common way of representing the average score in a particular group of scores. It's relatively easy to calculate, so hopefully you would agree with me on that it's relatively simple to calculate, and it's also easy to understand because it's so common. And another good thing about it is that it represents all of the data. It's a way of encapsulating the average score, considering every single observation, considering all of the data. While that's a good thing, that can also be a bad thing that I'll talk about a little bit later, in that it gets very easily affected by extreme scores. So if we had a particular extreme score, say we had this distribution of scores and then some person who was 75, the mean gets quite affected or skewed by having that particular extreme score. One of the other detriments to the mean is that it's not actually always a particular score in the data set. So what I mean by that is, in this instance, our mean score is 21 and we happen to have an observation of 21. That's not always the case though. So because the mean is a calculation using all of the scores, it's not always an actual score that happens in our data. The next thing I want to talk about is the median. And the median is a similar concept to the mean, but it's slightly less common, and the way of calculating the median involves ranking the data. So let's say we've got the exact same spread of scores here. What the median is the middlemost score if you rank all of your scores from smallest to biggest, from lowest to highest. So here I've done that exact same, I've done the same representation of the data in the first line, except here they just ranked from lowest to highest. So 17, 18, 19, 19, 21, 24, 29. So you rank the scores from lowest to highest, from smallest to biggest, and you pick out the middlemost score. So you can see that 19 is the score that falls in the middle there. There's 3 scores on the left and 3 scores above. So in this instance, 19 is our median age. It's the middlemost age. It's the one that's smack bang in the middle. If you have an even number of scores, then you're not actually going to get any one score that will fall in the middle. In that case, what you do is you take the mean of the 2 middlemost scores. So say we didn't have 29 there, then what we would do would be to take the average of 19 and 19, which happens to be 19. So if you have an even number of scores, you just take the arithmetic average, the mean of the 2 middle scores. One of the advantages of the mean is that, again, it's easy to find, so it's relatively easy to calculate it. And unlike the mean, it's not affected by extreme values. So if you have one score that's very, very unusual to the others' scores, the median isn't going to be particularly affected by that, other than the fact that it is one extra score. So it's not going to pull the median out like outliers pull the mean out. The disadvantage of the median is that it doesn't always best represent the data if you have a not particularly normal or clean shape distribution, if you have an unbalanced distribution. So the median doesn't always necessarily represent the kind of most typical part of the distribution. And just like the mean, it's not always an actual score in the data set. That's only if you have an even number of scores, it won't be an actual middle score in the data set. All right, the next one to talk about is the mode, and the mode is the easiest one to get your head around because it's just the most common value. So again, taking our same spread of scores we had before, the mode is just the score that occurs the most frequently, the one that happens to occur in your sample the most times. It's the most common score. So in this instance, our mode is 19 because we have 2 people whose ages are 19. All of the other, all of the other ages only happen once. They only occur once. You can have multiple modes. So if we had, say, another 21, then we would have 2 modes. We would have a mode of 19 and a mode of 21. So it is possible to have multiple modes. The advantage of the mode is that it's super easy, and it's always an actual score in your data set, unlike the median and the mean. Disadvantage is that obviously you can have multiple modes. So in terms of thinking about the best representation of the middle part of the distribution or the average of the distribution, having multiple modes is a bit of a disadvantage. And it also doesn't take into account all of the data. So it's not actually going to be considering all of the data in the way that the mean does. The next slide is just an illustration of the idea of that outlier. So what you can see here on the left-hand column of this table, or the second column of the table, the first fat column of the table, is the same scores that we've had over the previous few slides. And you can see, just like before, we've got a mean of 21, a median of 19, and a mode of 19. What I've done in the next column is just add one more score, which is a score of 78. So all of those 7 scores are exactly the same, plus we've added 78 there. And you can see that the mode is exactly the same. The mode doesn't change. The median has only gone up by 1 because we've added one more score, whereas the mean has increased by quite a lot. So when you have outliers, outliers being very extreme or unusual scores, the mean is the most affected measure of typicality in terms of how affected they are by those particular outliers. Okay, so that was the concept of typicality. The next concept is that of variability. So variability is a measure of how much variation, how much of a spread of scores there is, on how much dispersion in scores there is. It's kind of what's the range of scores, or how much variation or how much of a spread of scores is there in this particular sample. You can have scores that are tightly clustered together. So we could have, say, a sample of 10 students' ages and they could all be 18 or 19. That would be a very small variability. Or you could have scores that are very spread out. So we could have a sample of 10 students' ages that range from 17 through to 65, and they're quite well dispersed along that range. And it's possible to have the same mean or the same average score, but to have very different variability. And there's 4 different ways we're going to talk about in terms of measuring variability. The first is the range, then we've got an interquartile range, a standard deviation, which is the most common, and a variance. I think we actually do those the other way around. I think we do the variance before the standard deviation, but I think you'll survive with that. Okay, the first one we'll talk about is the range, and again, you're probably familiar with this concept already from high school maths. The range is super easy. It's just the difference between the smallest and the biggest score. So what is the actual distance between the smallest score and the biggest score? So you just literally do the biggest score minus the smallest score to get the range. So using these same spread of scores we had from before, you can see that our biggest score is 29, our smallest score is 17, so 29 minus 17 gives us a range of 12. So in this particular data set, we have a range of 12. An advantage of the range is that it's very easy to calculate. It gives you a good idea of what this is a very literal thing to say, but it gives you a good idea of the minimum and the maximum scores. So if you were looking at a sample of people who participate in a research project, looking at the minimum age and the maximum age gives you quite a good idea of obviously the ages of the people in the data set. So it can be very easy and it can be very representative. The disadvantage, or some of the disadvantages to the range, is that obviously it's very affected by extreme scores. So if you had, say, 10 people and they were all age 17 except for one who was age 60, then you'd have a massive range, even though that doesn't really represent the majority of the scores. The majority of the scores have very little variability. And it also doesn't take into account all of the data. So by its definition, it only thinks about the smallest score and the biggest score. The interquartile range is the next thing we'll talk about, which is a similar concept obviously to the range, but going back to this idea of ranking scores and looking at the difference between certain scores in those rank scores. So specifically the interquartile range is the discrepancy or the difference between the first quartile score and the third quartile score. So going back to our idea of a median from before, if we have this rank of our scores, if we start from the smallest score to the biggest score and we line them up in order, the median is the middlemost score, it's the one that falls in the middle, or the average of the two that fall in the middle if you have an even number of scores. If you then take the middle point on the left-hand side of the median, so you can see here our median is 19. On the left-hand side, we've got 17, 18, and 19. The middle of that is our score of 18, which becomes our first quartile. You do the same thing for the scores above the median, and so our third quartile here is 24. So a quartile is just 1/4 of the data. So we're just dividing our data into even chunks, 4 even chunks here. So the interquartile range, IQR, is the same thing as the range, but it's the third quartile minus the first quartile. So here it's 24 minus 18, which gives us an interquartile range of 6. Again, advantages is it's super easy to calculate. It's not affected by extreme scores like the range is, because it's kind of chopping off the ends of the distribution. At the same time, just like the median, it's not always an actual score in the data. And although it can give you a better representation of the spread of scores compared to the range, in terms of the spread of the majority of scores, sometimes it can be a little bit not representative in that case. Okay, the next thing we'll talk about is variance. Ignore those little symbols there, they were supposed to come out later, but I'm just going to leave them there for now. So variance and standard deviation, which is the next one that we'll talk about, are very similar because the standard deviation is just the square root of the variance. And what the variance is looking at the average distance of scores from the mean score. So on average, how far away from the mean scores are each of the other scores? That might sound like a bit of a weird thing to do, but we'll work through the formula of this similarly to the standard deviation on the next slide, and hopefully that'll become a bit more obvious to you what that actually means. The variability is denoted with an S squared when we're talking about a sample statistic, or the symbol for the population variance is this little, again, a Greek symbol, which is called sigma. So sigma squared is the population parameter of the variance. This is the formula for variability. Again, don't let it freak you out because it's a formula and it's got some italicized letters in there. It's really not that complicated, and so the next bit of information is just to work through, using a sample of scores, how we would actually work out that formula, how we would calculate that formula. These days, because we have computer programs to do kind of data description and summarising data for us, actually working these things out by hand isn't particularly common, but it is important for you guys to learn this just so that you understand the concepts behind what these metrics are telling us. So what we have here is, if you look at the first column, this is our age scores. This is the same scores we've been talking about all throughout the lecture so far. These are our particular scores for people's ages. The next column is representing the mean age. And so the mean, remember we calculated that earlier, was the mean age of 21. And if you have a look above the actual text there, you can see that age is represented by the symbol X with a little I subscript. XI just means any individual's score. I just stands for individual, so it's any particular person's score. X with a bar on it, we learned a few slides ago, is the mean age in our sample. So it's the mean score, the mean age in our sample. And if you go back to the formula on the left-hand side here, you can see that those are the two symbols that are inside the parentheses that then get squared. So the deviation is just the difference for each of our individual scores between that score and the mean age. And that's what's happening inside those parentheses in the formula. So each individual score minus the mean gives us a measure of deviation. Deviation is just distance from the mean. So you can see 17 minus 21 gives us -4, 18 minus 21 gives us -3, 21 minus 21 gives us a score of 0, a deviance of 0. So what you need to do to calculate this deviance score is to calculate that for each individual score. What is the difference between the value of this score and the mean score? So we calculate that. And then what we do, going back to this formula, is to square all of those deviances. So each deviance squared is what the next column in this spreadsheet becomes. So the deviation squared is just that individual deviance score squared. So -4 squared is 16, -3 squared is 9, -2 squared is 4, etc., etc. And then what we do, again going back to the formula on the left here, is to sum all these scores up. So to add them all up, add up all of the deviation squared scores. And that's what this big, it's called a capital sigma score on the left-hand side here. That's what that means. It's just saying that you're summing up all of the individual scores, all of the individual deviance scores. So if we sum up each of these deviation squared scores, then we get to a value of 106 in this particular sample. And then going back to the formula here, you can see what we do is then divide that by n minus 1. And n is a representation of our sample size. It's how many observations we've got, how many participants we've got here. So n minus 1, in this case n is 7 because we have 7 observations. 7 minus 1 gives us 6. So 106 divided by 6 gives us a score of 17.67. And 17.67 is our variance score. It's the measure of variance in this particular sample. And the bigger that variance score is, just the same as standard deviation on the next slide, the more variation around the mean there is, the greater the discrepancy between each of our individual scores and the mean score. The more spread of scores, the greater is the spread of scores. There we go, with a yellow box around it. The advantage of the variability is that it's easy-ish to calculate. You'd probably disagree with me on that, but compared to, I guess, some other things, it's relatively easy to calculate. You can get computer programs to do it for you, so Stata will very happily give you a variance score for any particular set of data. Again, it's very widely used, so it's very widely understood. People tend to know what a variance is, just like a standard deviation. And it takes all of our data into account. So it's a measure of the average deviation from the mean, which means it takes every single score, every single observation into account. The disadvantages, like we've talked about previously, is that it can be affected by extreme scores. So if you have one very, very different score, that's going to blow out your variability, your variance. So that is something to take into account. But it is a very commonly used measure of spread of scores, of variance of scores. The next thing to talk about is the standard deviation, and the standard deviation is exactly the same as the variance, but it's the square root of the variance. So the variance is the standard deviation squared, the standard deviation is the square root of the variance. So just like I said before, the standard deviation is the average deviation, distance of scores, from the mean scores. Standard deviation is denoted with an S in terms of a sample statistic, or the lowercase sigma for our population parameter. This is the formula for our standard deviation. You can see it's just the same as the variance formula, except it's got a huge square root symbol around it. And so going through the same process that we had on the previous slide, if you calculate the variance here, just like we did previously, and we got a variance of 17.67, and then we take the square root of that, that gives us a standard deviation of 4.2. So what the standard deviation is doing, it's kind of undoing the fact that we had to square all our scores before. So by taking the square root at the end, it's kind of undoing the fact that we had to square our scores before. So it's just representing the same thing that the variance is doing. It's just going to be a smaller number because it's square rooted variance. Standard deviation is also hugely well understood. It's more common than the variance actually in terms of what papers report or in terms of what people report to summarise data. So it's relatively easy. Again, you might disagree with me on that, but it's relatively easy to calculate, and again, it takes all the data into account. Same as the variance, one of the disadvantages is that it can be affected by extreme scores because it's taking all of the data into account. In terms of what are the most commonly reported summary statistics for numeric variables, the mean and the standard deviation by far. I'm sure you've seen it yourself in academic papers that you might have read for your studies so far, or you will be throughout the rest of this semester, that when papers are reporting scores, sort of 99% of them are reporting the mean and the standard deviation. The next slide is just to show you the difference between the range and the standard deviation in terms of representing the spread of scores. So what you can see here, this is just taken from your textbook. What you can see here is two different spread of scores. The top one, A, you can see that a lot of the scores are clustered around the 50, 60, 70 mark, and there's just one down at 30, one just above 100, and then one just above 140. Whereas the bottom part of the diagram B, you can see that the scores are much more spread out. There is much more even dispersion or even spread of scores all along the range. And what you can see here is that if we were to calculate the range, that measure of the biggest score minus the smallest score, the range between those two things is actually identical. So both of those two sets of scores have the exact same range. It's going to be 140 something minus 20 something. However, the standard deviation is going to be really different because remember that the standard deviation takes into account the average distance of a score from the mean. And so because in the top 1A, the scores on the most part are quite tightly clustered together, the standard deviation is going to be smaller than the bottom one because the scores tend to be more spread out. Okay, so that's a representation of the difference between the range and the standard deviation. And we are all very clever. Thank you, Willy Wonka.